Hi everyone. This is NLP Corgi. Today's deep dive is about the paper from Peking University and Google Cloud AI Research, PaperBanana, Automating Academic Illustration for AI Scientists. Modern language models can already help with literature review, coding, and even running experiments. But when it comes to turning those results into clear, publication-ready figures, most researchers are still stuck in PowerPoint or TIC-Z. Methodology diagrams and statistical plots are slow to create, easy to get wrong, and demand design skills many scientists don't have. That gap between automated discovery and manual illustration is now a real bottleneck for communicating new ideas. PaperBanana is a full agentic system designed to close that gap. It takes in your method description and figure caption and automatically produces publication-style methodology diagrams. The same pipeline can also generate statistical plots from data. Under the hood, it orchestrates vision language models with image generators and code generators, so the system can both understand your method and render it as a polished figure. The task is formalized very simply. The source context S is the method description, and the communicative intent C is the figure caption that says what the figure should focus on. Optionally, we can provide reference examples, triplets of context, caption, and human-drawn figure. The goal is to map S and C plus any references into an image I that accurately reflects the method, matches the caption's scope, and is easy to read. PaperBanana breaks the problem into two stages. First, a linear planning phase retrieves relevant reference figures, then plans the content of the new figure and polishes its style description. Second, an iterative refinement loop alternates between visualizing that description and critiquing the result, improving it over several rounds. The same architecture works for both methodology diagrams and statistical plots, with only the visualization mechanism changing. The retriever agent's job is to find good examples to learn from. It looks into a reference set of real NeurIPS methodology diagrams and uses a vision language model to rank candidates. The ranking emphasizes two things: matching the research domain like agents or vision, and matching the diagram type like a pipeline or architecture. Structural similarity matters more than exact topic, because the goal is to show the model what kind of visual layout to emulate. Next, the planner agent acts as the system's brain. It reads the method section, the caption, and the retrieved examples, then writes a detailed textual blueprint of the desired figure. This blueprint spells out what modules should appear, how they connect, and how the overall flow should be organized. It's not yet an image, but it's a precise, structured description that an image generator can follow. The stylist agent is responsible for making the figure look like it belongs in a modern NeurIPS paper. It scans the entire reference collection and automatically summarizes a style guide, which pastel backgrounds are common, how rounded rectangles and arrows are used, how fonts and math notation are styled, and so on. Using this guide, it rewrites the planner's blueprint into a stylistically optimized description that still preserves the original content. Once the description is ready, the visualizer agent renders it. For methodology diagrams, it calls an image generation model like PaperBanana Pro. For statistical plots, it instead writes and runs matplotlib code to guarantee numerical accuracy. The critic agent then inspects the generated figure against the original method text and caption, looking for missing modules, wrong connections, or visual issues. It updates the description, and the loop repeats for 3 rounds, steadily improving both faithfulness and aesthetics. To evaluate all of this rigorously, the authors built PaperBanana Bench, a dedicated benchmark for methodology diagrams. They started from thousands of NeurIPS 2025 papers, automatically parsed method sections and figures, then manually cleaned and filtered the data. The final benchmark has 584 high-quality diagrams, split evenly into a test set and a reference set for retrieval. Each diagram is also categorized into agents and reasoning, vision and perception, generative and learning, or science and applications. Evaluating diagrams is subjective, so the authors use a vision language model as a judge. For each test case, the judge sees the method text, the caption, the human diagram, and the model diagram. It then decides which one wins on 4 dimensions: faithfulness to the method, conciseness, readability, and aesthetics. Faithfulness and readability are treated as primary. If one diagram clearly wins there, it wins overall. Only if those are tied do conciseness and aesthetics break the tie. This keeps truth and clarity ahead of pure style. To make sure the VLM judge is trustworthy, the authors ran 2 validation steps. First, they compared its scores to those from other models, like Gemini Flash and GPT-5, and found moderate to strong rate correlations across all metrics. Second, they asked human experts to score a subset of diagrams using the same rubrics, then compared those scores to the VLMs. Again, the correlations were in a similar range. This suggests the automated judge is reasonably aligned with both other models and human perception. On PaperBanana Bench, the framework clearly outperforms strong baselines. Using PaperBanana Pro as the image generator, the vanilla prompt-only setup scores about 43 overall, while PaperBanana reaches just over 60. It improves faithfulness slightly, but makes very large gains in conciseness, readability, and aesthetics. Human diagrams are normalized to a score of 50 on each dimension. Interestingly, PaperBanana exceeds human style scores, while still trailing slightly in fine-grained faithfulness. The ablation study teases apart what each agent contributes. Without any retrieval, the planner tends to produce verbose, cluttered descriptions, and the resulting diagrams are less concise, less readable, and less polished. Interestingly, even random retrieval helps almost as much as semantic retrieval, suggesting that seeing any academic diagrams teaches the model useful structural and stylistic patterns. The stylist agent makes diagrams cleaner and better looking, but can accidentally drop technical details. The critic agent then plays a key role in restoring faithfulness while keeping the stylistic gains. For statistical plots, PaperBanana keeps the same high-level pipeline but swaps how visualization works. Instead of generating an image directly, the visualizer writes matplotlib code that renders the plot from raw data. The authors repurpose the chart-mimic dataset to build a 240-case test set with diverse plot types and difficulty levels. On this benchmark, PaperBanana consistently beats a strong baseline that uses Gemini 3 Pro alone, improving faithfulness, conciseness, readability, and aesthetics, and even slightly surpassing human plots on the style-related dimensions. The authors also compare two ways of drawing plots, directly with an image model or via code. Image generation tends to produce more visually appealing plots, but it struggles with dense or complex data. It can hallucinate values, duplicate categories, or distort bar heights. Code-based plots, by contrast, are much more reliable on the numbers. The takeaway is that a hybrid strategy makes sense. Use image generation for simple, sparse visualizations where aesthetics dominate, and fall back to code for dense or high-stakes quantitative plots. PaperBanana isn't just for generating new figures. The authors also test whether its Learn Style Guide can improve existing human diagrams. They ask a VLM to propose up to 10 concrete edits, like better color schemes, cleaner typography, or simplified shapes, and then apply those edits with PaperBanana Pro. When compared back to the original human figures, the refined versions win on aesthetics in about 56% of cases, lose in 37%, and tie in the rest. So the style guide can often make real diagrams look more modern and polished. Despite its strengths, PaperBanana still lags behind humans on fine-grained faithfulness. The most common failure mode is connectivity, arrows that start or end at the wrong node, missing generative links, or extra connections that aren't in the method. These errors can be subtle and are often missed by the critic agent, which reflects current limitations in visual perception for foundation models. Closing this gap will likely require better underlying vision language models, not just better prompting. Two broader limitations stand out. First, PaperBanana outputs raster images, even at high resolution, which are hard to edit precisely. The authors discuss possible solutions, like reconstructing figures into editable slide elements using OCR and segmentation, or even training GUI agents to operate tools like Adobe Illustrator directly. Second, the unified style guide that enforces a NeurIPS-like look can also narrow stylistic diversity. Future work could let users dial in different style families while still staying within professional norms. The evaluation setup also has limits. Even with careful prompts, a VLM judge can miss subtle structural errors, like slightly miswired graphs, and aesthetics are inherently subjective. The authors suggest richer, structure-aware metrics, and possibly learned reward models for style. They also point out that generating just one figure per query is restrictive. A more powerful approach is test time scaling. Generate a diverse set of candidates, then let humans or preference models pick the one that best fits their needs. Stepping back, PaperBanana is a concrete example of how agentic pipelines can tackle complex, high-stakes visual tasks. By separating what to draw from how to draw it, and grounding both in real reference figures, the system generalizes across methods and even across diagram types. The same paradigm could extend well beyond academic papers, to domains like UI, UX design, patent drawings, or industrial schematics. where strict community standards meet rich visual structure. For now, it already moves us closer to AI scientists that can not only discover ideas, but also communicate them visually at a professional level.